allowed to bring a single 3x5 card. That's 3" by 5". And you can put anything on it that you want if there is something you're having difficulty remembering or whatever. This exam, I think, came up to 146 points. I will strive to make the real exam 150 like it's supposed to be. And there'll probably be an extra credit on there, but I'm not sure yet. All right. Starting off with some very simple nomenclature. Here we have a di-substituted benzene. We recall that we want to assign carbon number 1 in a case like this alphabetically. That means that ethyl is going to win, so that's going to be carbon number 1. At carbon number 3 we have a methyl group, and of course our parent is simply benzene. Ethyl 1, methyl 3, the name we put together, 1-ethyl, 3-methyl benzene. You can also name this as a derivative of toluene. Either one would be acceptable. Remember, if you name it as a toluene, the methyl group is automatically carbon 1, which makes this 3-ethyl toluene. Next guy here, tri-substituted benzene. In this case, we want to number this so that we get the lowest number sequence. That means our nitro group is going to be carbon number 1. We're going to proceed counterclockwise around the ring numbering. So we'll have a bromine here in carbon 2, a methyl in carbon 4. Going to put the name together alphabetically, so it would be 2-bromo. Methyl comes next, right? So that's 4-methyl, 1-nitro benzene. And our last nomenclature here. This is not toluene. No, we're missing a double bond, isn't it? So this is a diene. Our parent here is going to be a cyclohexadiene. Remember, we want to start numbering at one end of our diene. We want to proceed through our double bonds, which means that the lowest number sequence we get is if we start numbering out here. As we go around this way, that puts our methyl group down here in position 5. We need to indicate that this is a 1,3 cyclohexadiene. So our name, 5-methyl, 1,3 cyclohexadiene.
Dr. Young.
Yeah.
I don't know if this is retarded, but is cyclohexatriene something? Could you, or is that?
Cyclohexatriene is benzene.
Okay, so I could, is that okay? So I wrote that down a couple of times. I put benzene.
No, don't do benzene.
Oh, you got it.
All right. This is followed by a series of multiple choice questions. Which of the following is true regarding a C13 NMR of carbonyl compounds? All right, remember in this C13 NMR, carbonyls are going to be very highly shifted. Children can be relentless, you know.
Jesus. Just buy the new car.
Carbonyl carbons are very highly shifted. Ketones and aldehydes are the most highly. They're around 200-ish. Oh, how about that one right there? Acyl carbonyls, that is, esters, amides, things like that, are lower in the 170 region. So let's take a look at these. Proton coupled, so that means we're going to get splitting here. We're dealing with an aldehyde, that means we have a hydrogen attached to the carbonyl carbon, which means that the carbonyl signal will in fact be split into a doublet. Again, they typically absorb around 200. There is no hydrogen attached to a ketone, is there? Therefore, that must be a singlet. A and C sounds to me like A, B, and C all work.
Is this being recorded?
Yeah. All right, chlorine, mass spec. We have two isotopes of chlorine, chlorine 35 and chlorine 37. Chlorine 35 is roughly 75%, 37 about 25%. If we have a compound with a single chlorine atom, its molecular ion will have both of these isotopes and the ratio 3 to 1. If we look at the mass spec of toluene, what are we going to see? Well, when you put toluene into a mass spec, the first thing you're going to form here is this guy. This is our molecular ion, isn't it? It's just lost an electron. It's the radical cation. So that's not it. If we lose a hydrogen off of this, we would form the benzyl carbocation. So that's reasonable. The phenyl carbocation is not, because that's very unstable. And the phenyl radical cation is really no more stable than this guy. Benzyl carbocation is our most stable, no question about that. But remember, benzyl always rearranges very, very quickly to form tropylium.
So it goes from A to C to B?
I'm sorry?
So it goes from A to C to B?
Yeah, it goes from here, well, from A to C to B. This is our base B.
Okay.
Benzyl alcohol, what are we going to see in the IR? We would expect nice big broad OH peak, around 3,400-ish. We would expect sp squared hydrogens. We would expect sp cubed hydrogens. No triple bonds, no carbonyls, and we'd also expect aromatic carbon-carbon double bond stretchings. So we're looking for something with a 3,400. So these guys are good. 3,100-ish. So those guys are good. About 29 or so. That looks good. And our carbon-carbon double bond would be right there at 1,600. The one that works for the set is this.
What's the 1760?
I'm sorry?
What is 1760?
1710. No, that would be a carbonyl. Remember, carbonyls are between 17 and 1800. All right, if we're looking at methylbenzyl nitrile, we have a nitrile group here, that's a carbon-nitrogen triple bond, and we have our benzene ring. In the proton NMR, the phenyl group will appear as two doublets. Well, we have a 1,4 disubstituted, and they're different. So that means we have two different types of ring hydrogens. We'll call it A and B. A will split B into a doublet. B will split A into a doublet. So yes, we get two doublets. That's true. The C13 NMR will have two singlets and two doublets in the aromatic region. Well, these two would be singlets, wouldn't they? And they are different. We have another doublet for these two, another doublet for these two, because they each have a hydrogen attached, remember. So that's good. Peak at 2200 reciprocal centimeters. That is our triple bond stretch. In the proton NMR, the methyl group, that's this guy, will absorb at about 2.2-ish. That's about where you get a methyl attached to a benzene ring. So yeah, that's good. And finally, in the mass spec, the base peak will most likely be at 91. Well, we do have a benzene ring and we do have a methyl group, but there is no way you can clip something off here and form the tropylium ion. No way.
Can you say what you said about B again?
I'm sorry?
Can you say whatever you said about B?
B?
Yeah. Isn't that tropium?
That would be tropylium, right? And we can't form it. B. All right, look at our C13 NMR in the aromatic region. We have two different singlets here, right?
Yeah.
Because they have no hydrogens, they will both be singlets and they will be different. These two hydrogens are identical, or two carbons are identical. They're each attached to a hydrogen, so this will be a doublet. These two carbons right here are also identical, plane of symmetry right through here. These two are identical, they have a hydrogen, so they will both appear as doublets. Two singlets, two doublets. Yeah.
For C, so the 2200 could be a CN, a CC, or a triple line, like all three of them?
Yeah, well, could be a carbon-carbon triple bond,
Right.
or a carbon-nitrogen triple bond. Carbon-nitrogen triple bond really shows up nicely. Big, sharp thing. Remember, carbon-carbon triple bonds typically are four.
Okay.
All right, which of these would be consistent with the C13 spectral data shown here? There are several ways you can look at this. Let's just run down through our list here, first of all, and just get a feel for what these things are. Our quartet here, that's going to be a methyl group, isn't it? Our triplet is going to be a CH2. This quartet is also a methyl group. So we have two different methyl groups and a CH2. We have a singlet here at 172. That's where we typically get acyl carbonyls. And we also have a singlet at 207. That should scream at you ketone carbonyl. So what we're looking at, or looking for here, is something with two methyls, a CH2, and two different carbonyls. Now if you think about it this way, we do have two methyls here, only one type of carbonyl though, right? That one's out. We have 1, 2, 3 types of methyls here, so that's out. Here we have two methyls and we have two carbonyls, don't we? This would be an acyl, this would be a ketone, but we're missing our CH2. That's our triplet here. This is out altogether. Again, this would be a acyl carbonyl around 170-ish, but we have nothing in the benzene ring region. The only one that works here is going to be this guy. Here we have two different methyls. We have a CH2 in the middle. We have a ketone carbonyl and an acyl carbonyl.
It's an
Acyl, this is an ester, acid, acid halide, all of those sorts of things. Those are acyl.
Can you tell me what ester?
I'm sorry?
Okay, can you tell me what ester?
The,
Ester?
right, this is the carboxylic ester, and this is the one at 172. All right, here we have C13 NMR, a symmetrical 1,2 disubstituted benzene. We want to, let's see, we're looking at the native spectrum, so not decoupled. So we're going to see multiples here. When you look at this compound, what you want to do is decide is there symmetry. Because this is symmetrical, 1, 2, we have a plane of symmetry right across the middle. Okay? That means that everything on the top is identical to everything on the bottom. Now all you have to do is just ask yourself, how many different carbons do we have? And how many hydrogens are they attached to? This guy here, no hydrogen, that would be a singlet. This has a hydrogen, it's a doublet. This has a hydrogen, it's a doublet. We would get 1 singlet and 2 doublets. Yeah.
I have a question about that. I get kind of confused with the whole plane of symmetry thing. About how, I guess how it plays into what you get if you have a plane of symmetry. Like,
Well, if you have a plane of symmetry, as far as NMR is concerned, we call those things magnetically equivalent. So this carbon and this carbon are magnetically equivalent. If there's a plane of symmetry, they would be equivalent, so they have the same NMR signal.
so they don't have 2 peaks.
Right.
They're 1 peak.
It is one type of carbon. So that's it. Looking for symmetry is very important. We're going to have, actually coming up right now, we're going to have a bunch of simple problems looking at the number of peaks in the NMR. Very important that you practice your symmetry if you have trouble with that. Speaking of that, how many peaks for this guy?
2.
Well,
2.
sounds like 2 to me. The question is, how many types of carbons?
2.
Let's start here. That's obviously a unique carbon, isn't it? We have another one over here, but it's identical to that one, isn't it? Therefore, that one doesn't count. And this guy in the middle is unique, different than each of these. So we are stuck here with 2 different types of carbons, 2 peaks in the proton decoupled NMR. Remember, proton decoupled means we don't get splitting. Okay? How about this guy? Once again, let's look and just ask ourselves, how many types of carbons do we have? We have a carbon in between 2 oxygens. Doing the same exercise again. This is also a carbon between 2 oxygens, but it is magnetically equivalent to this one, so it doesn't count. If you go around the ring, all of these carbons are magnetically equivalent, and we get 1 peak. Now this one is drawn to deliberately confuse you. It's a trans ring junction. Again, we're looking to try to identify the numbers of carbons. Now, you should be able to look at this and say, yep, plane of symmetry here, plane of symmetry here, blah, blah, blah. If you have trouble doing that, just remember, you can draw the thing this way. Makes it even simpler. If you draw it this way, it's very obvious we have a plane of symmetry across and a plane of symmetry up and down. So in terms of unique carbons, our tertiary carbon here is 1. Here we have a carbon next to our tertiary. This guy is next to the secondary. 3 peaks in the NMR. Symmetry exercises can be really fun.
Symmetry exercises.
All right, we have an infrared spectrum. Which of the compounds shown below would be consistent with it? Now, frankly, as soon as you see this, it should scream at you. Now, what is screaming at you?
A lot of things. Carbon.
Aside from me. We have a big carbonyl here. All right, so we're looking for something with a carbonyl.
Aldehyde.
That's right. Our doublet here at 2750, where nothing else absorbs, is an aldehyde. So we have a carbonyl. We have an aldehyde. We have sp squared CH. We have sp cubed CH. And these guys here kind of look like a benzene ring, don't they? Classic sort of pattern for the carbon-carbon stretch. We run through the whole list. We have no OH. Nice sharp peak here for sp squared. A little thing there for sp cubed. Big, sharp aldehyde CH. This is the one that gives it away. No triple bond, nice carbonyl, and classic benzene ring here. This, of course, is 4-methyl benzaldehyde. Now here we have an NMR, and if you look at it, it can kind of make you nuts for a second.
Yes. Longer than a second.
Because this is a triplet, right? No problem. How many peaks here? 5. Oh my gosh. Oh my goodness. Well, it really isn't that much of a problem. This is worth 4 hydrogens. It's a triplet where, because we have 4 hydrogens, we're looking at 2 identical CH2 groups. When I say identical, once again, I mean magnetically equivalent CH2 groups. This guy here, because it's 5 peaks and worth 2, this is going to be a CH2, but it has to be next to 4 magnetically equivalent hydrogens. Now, we can't have a CH4, can we? But we can have 2 CH2s. Therefore, the one that's going to work here is this guy. Here's our CH2 in the middle. CH2 in the middle is adjacent to 1, 2, 3, 4 hydrogens. Therefore, it's split into 5 peaks. This guy, same as this guy, is next to a CH2, therefore they are both split into the same triplet. Any questions? All right, in order to be aromatic, compound must be planar, cyclic, consist of adjacent sp squared centers with 4n plus 2 pi electrons. Gee, Huckel couldn't have said that better himself, could he? So that's the classic definition of a aromatic system based on the Huckel theory. It must have at least 2 electrons in each of the degenerate molecular orbitals describing the pi system. You know, that has so many words in it, it sounds like it could be right, but of course it's nonsense. All heteroatoms must rehybridize so that all unshared pairs can contribute to the pi system? No. Now, we saw lots of heterocycles, remember? Things with hydrogens and oxygens in the ring, where the lone pairs would either be orthogonal to the ring plane, so they don't count, or they would participate in the pi system. They can do either, sometimes both, but all of them don't have to do it. This is the classic definition. All right, now that we know the classic definition, which of these meets it?
A.
Well, if we look at A, what was the first thing in the Huckel thing? It has to be cyclic, right? It's not cyclic. Our second one here looks really promising, except what's this here? That's an sp cubed carbon. That doesn't belong there. Remember, they must be adjacent sp squared carbons, all conjugated together. How about this guy? Well, it is conjugated, it is planar, and it has 2, 4, 6, 8 pi electrons. Is that a Huckel number?
Negative.
No! This guy down here. It is conjugated. It is planar. And it has 4 pi electrons. Is that a Huckel number? No. So which one works here? This is simply a benzene ring, isn't it? It's got this stuff attached, but this is a benzene ring. 6 pi electrons, aromatic.
How does that? That's so confusing.
I mean, you just got stuff attached to it. It's still a benzene ring, isn't it?
I don't know. It's
Yeah.
So for C, so there's four pi bonds, right?
Right. So 8 electrons. That is not a Huckel number. 4n plus 2. Huckel goes 6,
Is it
10, 14, blah, blah, blah.
Yeah, but then wouldn't the plus 2 be 2 more or not?
You just use any number, like you plug in 0, so that would be 2. 0 plus 2 is 2.
So n is 2. You need 10
That's
electrons.
how many electrons.
Oh, so
You don't add it to this.
Yeah.
So does C have a sp3 carbon because it's a
Nope.
little connection?
Nope, these are all sp squared carbons.
How do we know this D is planar?
What about the one in the middle? That's just.
This guy? That's sp squared, so what's that?
It has nothing to do with
What about
So you're not
the
plugging it for there?
attachment?
You're not plugging it, you're plugging
I
it
need
in
to
zero.
attach it in now.
You have to add it up, whatever
Yep.
this is.
Especially with an actual.
All
with
the way
actual
around.
work on it.
could be like this
So this is the electric, which is not.
I have a question.
Yeah,
Oh, I thought it
How do we know like D is planar?
Hmm?
How do we know D is planar?
You don't plug this.
this guy?
It's separate.
Yeah, how come we
That's a
wouldn't,
benzene ring.
we wouldn't consider this attachment at all?
No, you just look at it, you say, oh my goodness, it's a substitute.
It has to be one of those numbers, so if you're putting zero, that's, it's not.
All right, let's look at this again. We talked about things being anti-aromatic.
So this is
Now, in order to be anti-aromatic, it must meet all of the Huckel rules except have the wrong number of electrons. So it must be planar, must be conjugated, must be sp squared all the way around, but it has the wrong number of electrons. Once again, this is not cyclic. Once again, we have an sp cubed carbon.
C.
You'll note down here, this guy has changed from the previous slide. This is now an anion. Previous slide, it was a cation. This guy here, we already know this is aromatic. This guy here now has 2, 4, 6 electrons, and it's also aromatic. So the one that is anti-aromatic is going to be this guy. Once again, it has 8 pi electrons. That's not a Huckel number, but it is planar and conjugated. Any questions?
So you're telling me the attachment does not change it from being planar?
Nope, 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 nope,
Take your word.
nope. I mean, if we just took all the substituents off, it would be just a plain old benzene ring, right?
Yeah.
If we add just this thing, the arm at the bottom, that would be styrene. Still, plain old benzene ring. Up here, this is just an ether attachment. Still a benzene ring. Not going to change the heart of the ring at all. Yeah.
How does E become aromatic? Because I know you
E?
explained that. Yeah, I just.
Well, look at your sheet. In the one before, this was a carbocation, right? That means that it had only 4 pi electrons. Now we've made it the cyclopentadienyl anion, it's called. So it has 2, 4, 6 pi electrons, planar, conjugated, aromatic. You can draw resonance forms where you put this lone pair on every carbon. We did that. All right, there will be a mechanisms problem. Now, you don't know very many mechanisms, so this really shouldn't be real challenging. This is simply the mechanism for electrophilic aromatic substitution, and we're doing Friedel-Crafts alkylation. First thing you're asked to do here is to draw the structure of the electrophile in complex with the Lewis acid. So that's this guy. Bromomethane, Lewis acid is iron 3 bromide.
Mine's different. I have CH3Cl, AlCl3. Does it matter?
Really?
Me too. That's why I didn't do it. 'Cause
Huh.
I looked at it.
Okay, well, just pretend that you have the same thing I do.
It changes.
Change everything. The structure of the electrophile. Remember, the bromine is going to coordinate with the iron 3, the Lewis acid. We're going to form some sort of a complex like this. We're not going to form a free carbocation because methyl carbocation would be too unstable. But in this complex, we have a carbocation-like methyl group. So you simply draw this in your little box. Now, our intermediate sigma complex, also called a Meisenheimer complex, what we're going to do is simply take our electrophile or methyl group and we're going to add it to one of the ring carbons. When we do this, we generate a carbocation on the adjacent carbon in the ring. And it should look something like this. Methyl group adds carbocation adjacent to it. Now we know that we can resonance stabilize this. We resonance stabilize it, putting the positive charge down here and over here. You're simply asked to draw one additional major resonance form. All you had to do that is to move this pair of electrons up and draw the other resonance form. There are 3 total. This is 2. And finally, to get our final product, a base comes along, pulls the hydrogen off, electrons go back into the ring, and we have made toluene. The only 2 mechanisms that we've talked about, really, well, I guess 3 mechanisms. 1,2 and 1,4 substitution in a diene, electrophilic aromatic substitution, and nucleophilic aromatic substitution. So we have 3 mechanisms. You will have one of them on your exam. Any questions? All right, simple reactions. We don't know very many reactions, but we'll do the ones that we do know.
My video broke down, Dr. Young, what was the 3 mechanism again?
The 3 mechanisms. Well, we talked about 1,4 and 1,2 substitution on a conjugated diene. We talked about electrophilic aromatic substitution, and we talked about nucleophilic aromatic substitution. Only 3 we've done. All right. Our first reaction here, we're doing electrophilic aromatic substitution. We have bromine, iron 3 bromide. Our electrophile is going to be Br+. This is toluene. So our ring is activated, and the methyl group, we recall, will direct ortho and para to itself. All you have to do is draw one of the isomers, just for simplicity. I typically will draw the para isomer. Permanganate. We recall that if you have a benzylic hydrogen, you must have a benzylic hydrogen, that neutral permanganate and a little bit of heat will oxidize the carbon here all the way down to the carboxylic acid. Doesn't matter what else is attached. If you have a benzylic hydrogen, you will get benzoic acid. Our next one is also electrophilic aromatic substitution. Here we're adding an ethyl group to the ring. Once again, this is going to be ortho-para directing. Therefore, we're going to stick the ethyl group down here in the para position. You could draw it ortho, that would work. And this is our product. Our next one, we're doing nitration, aren't we? We have nitric sulfuric acid mixture. Our electrophile is going to be NO2+. We still recall that even though we're putting on a nitro group, the methyl group is still going to direct it down here, para to itself, ortho and para. The product of the reaction would simply be the 4-nitro-toluene. Now, this is how you make TNT, obviously. If you take this mixture and you just let it sit, you actually get tri-substitution. Put another methyl or nitro group here, another one here. That is tri-nitro-toluene. Our next reaction here is the Friedel-Crafts acylation. Remember, in the Friedel-Crafts acylation, we're using it, or we're actually adding an acylium-like ion directly to the ring. It's going to add through the carbonyl here. Again, it's going to be ortho and para, and that would be our product. Finally, N-bromo-6-cinnamide, carbon tap, light. This is free radical bromination, isn't it? Going all the way back to chapter 10 or so. What this will do is to form the benzyl radical, which is very stable. Then it will attach a bromine to that, and we'll simply make benzyl bromide. All right, our spectroscopy problem. Start off, look at our formula here. C9H10O. How many degrees of unsaturation?
4.
We have 5 degrees of unsaturation. Quite obviously, we're talking about a benzene ring of some sort. If we look at our mass spec, this stuff weighs 134. Here we are at 134. That's our molecular ion. Our base peak here, we take our molecular ion. Base peak is 119. That is M minus 15. So we have a methyl group that we can clip out and form something stable. If we take our molecular ion here and we clip out 43, we would get 91. And we do have a peak here. But this probably is not going to be tropylium, is it? Because when you can form a tropylium ion, it's almost always the base peak because it's so stable. So we can do an M minus 43. So we're dealing with loss of an acylium or an isopropyl. Everyone happy with this? Simply writing this down on the exam, these guys here, you've got 5 points. Infrared. Let's start up here at the high end. We have no OH peak at 3400. We have a nice sharp peak here just on the high side of 3000 for SP squared CH. We have a couple really nice peaks here at about 29 or so for SP cubed CH. These are too high to be aldehyde peaks. Remember we saw an aldehyde, that'll be about here, 2750 or so. We have nothing in the triple bond region. We have a nice happy carbonyl. And we have a bunch of peaks, 1600 and its friends, consistent with arene carbon-carbon double bond. So what it looks like is we have a benzene ring and we have a ketone. We know it's a ketone, not an aldehyde, because we don't have the aldehyde stretch.
Where does the aldehyde stretch?
2750. Look at the previous problem, beautiful example of it. That's why I chose that problem. All right, proton and C13 NMR. Our proton NMR. Down here, this is our benzene region, isn't it? We have 2 doublets worth 2 hydrogens each. One of the things, really the 2 things you want to remember for the benzene region. If we have a messy singlet or a multiplet or whatever, that's either monosubstituted or 1,2, 1,3, whatever. If we have 2 beautiful doublets, that tells you it is para-substituted. All right, so this looks like para-substituted aromatic with different things on each end, okay? Down here we have 2 triplets. They're both worth 3. So that tells us we have 2 different methyl groups. They're not adjacent to anything with a hydrogen. They're just simple methyl groups. Two singlets, 3 hydrogens each. We have 2 different methyl groups, 2 doublets in the benzene, para-substitution. Our C13, 196 singlet. That's our ketone carbonyl, isn't it? We have a singlet and 3 doublets. I'm sorry, we have 2 singlets and 2 doublets. That is what you would get for para-disubstitution. Each singlet is from the opposite ends of the molecule, and these 2 doublets are the CHs in the middle.
Sorry, I'm a little confused. The singlets, I thought that meant that there were no hydrogens adjacent, but you said 3 hydrogens each.
We have 2 singlets of these guys. Right,
But
there are no hydrogens adjacent, but this peak is worth 3 hydrogens. Remember, the integration tells you the number of hydrogens. And finally, we have 2 quartets down here. Again, 2 different methyls. All right, put it all together. We know we have a ketone. The M-43 makes sense if it's a psyllium ion that we're clipping out, right? This would also give us the methyl group, isolated methyl next to a carbonyl. We know we have two different methyl groups. One of them is this guy that's next to the carbonyl. There's only one other place on the ring to put it. It's got to be 1,4 substitution. It has to be this. Now think about your C13 NMR. In the benzene region, we had two singlets, right? So this guy and this guy, no hydrogens attached, they're singlets. And they're different. We have a plane of symmetry. So this and this are the same, this and this are the same. This has one hydrogen attached, so it's a doublet. This is a doublet. C13, two singlets, two doublets. Any questions?
Can you go back to what the C13 shows? Like, yeah.
C13, all right?
Yeah.
You've got the thing on your sheet, so I'll just say, in our benzene region, we have two singlets, don't we? This guy and this guy. They don't have hydrogens attached, and they're different carbons, because they have different things attached to them. Therefore, they will be two distinct singlets. This carbon and this carbon each have one hydrogen attached, so they will be doublets. But they're different. This is next to the methyl, this is next to the ketone. So one doublet, a second doublet, one singlet, a second singlet. And of course, we have two different methyls. Alternatively, you could just sit down and draw all the possible isomers of C9H10O that have para-substitution. I think there's only one way you can do it, to be honest. Any questions? All right, 4+2 cycloadditions. We know we're going to react a diene and a dienophile. We know that this is going to give us a 6-membered ring, right? 4 plus 2. The stereochemistry of the dienophile is preserved. So here we have trans stereochemistry. That means in our product, we will have trans nitrile groups. You could draw this any number of ways. Something like this should work. Here's our 6-membered ring. You simply need to make sure you show that our two nitrile groups are trans. All right, this next one sometimes confuses people. This is our dienophile, isn't it? Just a double bond. It's got stuff attached to it, but we don't care. And this is our diene. All we're going to do is add this and this together and make a 6-membered ring, right? With a double bond in the middle. And the rest of this is just going to go along for the ride. The product would look like this. Here's our dienophile. These are the bonds that we made in the reaction. And our last one here. Now our diene is a 5-membered ring. We are adding a simple dienophile to it. Remember, all in the world we're going to do is make a bond from each end of our dienophile to this carbon and this carbon. Because this is a cyclic diene, we will wind up with a bicyclic product. The bonds we made, these are the carbons that used to be the dienophile, these guys, these are the bonds we made in the reaction. Here you can see our 5-membered ring. All we did is make a bond, this carbon to here, this carbon to here. All right, again, we have a cyclic diene. And we have a cis dienophile. Now we know that that means that we will wind up with these two cis to each other. Because that's stereochemistry dessert. Remember that. This reaction, again, is going to go from the 2 carbons of our dienophile to this and this on the diene. Just like that. Okay? Now there are 2 ways you could draw this product. We're going to make a 6-membered ring here. So that's 1, 2, 3, 4, 5, 6. Double bond's going to be in the middle here. Remember, when these things line up, the lowest energy position is to put these things with their pi system so they overlap this. That generates our endo-stereochemistry. So our product is going to look like this. Again, our 2 nitrile groups are cis, and they're pointing down here to where we made our double bond. Endo-stereochemistry. Here's a 6-membered ring we just made. Actually, these are in the wrong position, so let's ignore those. The bonds we just made are these and these. Ignore those wiggly lines. Our last one, we have a cyclic diene, and this is going to be our dienophile. We're going to wind up with a bicyclic product, so it's going to look like the one we had on the previous slide, except no oxygen. We just have the CH2 as our bridge. Sometimes people get confused here. If you do, just ignore everything that's attached to your double bond. Draw that in later. So you're going to make bonds from here and here to here and here. Oh, okay. I meant to say that. Ignore the wiggly lines though. So, the bonds that we just made here are these. So you draw this, And then you look and say, okay, what else is left over? CH2 and another double bond. Just ignore all this stuff, draw your basic structure, and then put it in. So now that we know all about endostereochemistry, I even put a second problem on here. Here we have a diene and a dienophile. We could make two possible isomers. You should look at these and say, well, here our pi system on the nitrile is pointing away from our pi system. Here it's pointing towards it. This is favorable. So we're going to get isomer number 2. And frankly, then, I ask you to use your words. This is always fun on an exam, to use your words. Why? Because the pi system here on our dienophile can interact with the pi system on the diene. And I think we wound up here with a couple simple multiple choice questions. One about electrophilic aromatic substitution and one about nucleophilic. Electrophilic aromatic substitution, what's true? In the intermediate sigma complex, the ring is no longer aromatic. Is that true?
No.
What's the hybridization of the carbon where the electrophile adds? It's sp cubed. To be aromatic, everything has to be sp squared. So that's good. This one's right. Nitro activates the ring. Nope. Nitro is down at the bottom of our list. It deactivates the ring. All sigma complexes are cationic. We take a nice, happy, neutral benzene, and we add something positive to it. Conservation of charge, sigma complex must be cationic. A and C are both correct. And finally, nucleophilic aromatic substitution. The intermediate sigma complex, the ring is no longer aromatic. Well, nucleophilic aromatic substitution, we're going to add something to it, aren't we? Once again, we're going to go from all sp squared carbons to one being sp cubed. So we lose our aromaticity. Nitro group activates toward the ring towards substitution at the meta positions. No. All sigma complexes are anionic. In nucleophilic substitution, you have a ring and you're adding something that's negative. It's neutral to start, then it goes negative. So everything is anionic. A and C is true. Remember, this is our basic mechanism. Anionic nucleophile attacks sp cubed carbon, so it is no longer aromatic, and it is anionic. Any questions? Remember, this is also called an addition elimination mechanism. And finally, on Wednesday, we get to do our addition elimination lab. So, whoa, that is exciting.
Quick
Yeah.
question. So for, it says a nitro group activates the ring towards, so you said that isn't true. So if it deactivates it, then that means that's why it's A and not right?
Go back, the activates at the meta positions. First of all, nitro group never activates. In this mechanism, you'll note that the nucleophile must add adjacent to the nitro group. That's so that the electrons can go here and be delocalized. So if you want to say nitro activates, it would activate ortho to itself. But never meta.
So that's highly reactive, right?
Hmm?
That's very reactive.
Yeah, well, it forms this complex. The reason, I mean, look at your notes. The reason that this is stable is that the electron pair is actually out of one of the nitro oxygens. It's not a carbanion, it's an oxyanion. Carbanions are bad, oxyanions, they kind of go oxide, that's good. All right, that's it.